Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this lecture number 13 of the course Stochastic Hydrology. If you recall, in the last lecture we dealt with data generation techniques, especially the stream flow generation using the first order Markov processes, and we introduced the for annual flow generation the first order Markov model. Recall that this will express x t using the lag 1 correlation and its which indicates its dependence on x t minus 1, and the model that we introduced will preserve the mean, the standard deviation and the correlations of the historical data. So, if you have annual series of stream flows, you can compute these moments and then use the model, the Markov model, first order Markov model, and generate series of annual flows. Then we relax the requirement that the series be stationary, and we considered the non-stationary first order Markov model, where for each of the month or a season you have different means, the standard deviations and the lag 1 correlations. We incorporated that into the Markov model and then introduced the non-stationary first order Markov model. This in the hydrologic literature is famously known as the Thomas Fairing model, and typically it is used for flow generation for monthly and seasonal time periods, and in some cases it has also been used for flow generation during smaller time intervals like 10-day time intervals and fortnightly time intervals, etc. Recall that the requirements for the Markov model as we introduced in the last lecture are that the flow time series can be approximated to be a Markov chain, and also that the flow series can be approximated to follow normal distribution. The Thomas Fairing model that we introduced in the last lecture requires the flows to follow normal distribution, and it also generates negative values because we are following the normal distribution, and in the applications the negative values are set to 0. If you are using the sequence that you generated using the Thomas Fairing model into, let us say, simulation of reservoir operation, at the time of applications you set the negative values to 0, but while using the generating model itself you keep the negative values to generate the next values. Because it generates negative values, often using the log transformation is advantageous. So, we also have the log transform Thomas Fairing model, where simply you transform the x t into log x t and use the Thomas Fairing model on the log x t series. That is also quite popularly applied in hydrologic literature. Now, we move to the next topic, which I introduced just towards the end of the last lecture. This is called as the frequency domain analysis. So far, whatever we have been doing on the time series analysis is on the time domain. For example, we calculate the correlations and then plot the correlogram. All of these are done with respect to time. We talk about correlation at a particular lag, and these lag that we considered are with respect to time. We can also transform the observed series x t into a frequency domain and then do the analysis in the frequency domain. And often this is very advantageous, especially in determining the periodicities inherent in the data. So, the frequency domain analysis we carry out mainly to identify the periodicities in the data. If you recall, we expressed x t, the time series, as consisting of d t, a deterministic component, plus epsilon t, which is a stochastic component. And right in the beginning, we mentioned that the d t, that is the deterministic component, can consist of, let us say, a long term mean around which the values are fluctuating, or you may have a trend, increasing or a decreasing trend around which the values are fluctuating, or you may have a periodicity like this around which the values are fluctuating randomly, apart from having a jump in the series and so on. Identification of these periodicities is an important problem in hydrology. The correlogram, as you can see here, if you have a periodic process, the correlogram will typically look like this. In the time domain, if you plot the correlogram R k versus k or rho k versus k, the periodic process will look like this. So, where the correlogram is oscillating periodically, and typically it dies down slowly in most of the hydrologic processes. The correlogram indicates that yes, there are periodicities inherent in the data, but identification of the exact periodicities and the significant periodicities inherent in the data is better done with the spectral analysis, where we transform the time series x t into the frequency domain, and then we analyze the time series in the frequency domain. This analysis is called as the spectral analysis. So, the periodicities in the data which were indicated by the correlogram can best be determined by analyzing the time series in the frequency domain, and such analysis is called as the spectral analysis or analysis in the frequency domain. The basic premise or the basic hypothesis with which we start is that the observed time series is a random sample of a process over time and is made up of oscillations of all possible frequencies. So, this is the basic premise on which the frequency domain analysis is based. And then we look at the time series as having been consisted of several frequencies, and then we look at which of these frequencies are dominant in the observed time series. The spectral analysis, as we introduce now, is widely used in several other fields also, like electrical engineering, physics, meteorology, apart from hydrology. In hydrology, specifically the applications of spectral analysis include dry and wet run analysis. Let us say you have a large sequence of rainfall data, and you would be interested in frequencies of dry periods or wet periods, periodicities of dry and wet periods. That is where we use the frequency domain analysis. We also use it for developing models for synthetic generation, in which we would be incorporating into the models the periodicities inherent in the data, and for that identification of periodicities becomes important. Even in the hydrologic forecasting models, when we are talking about medium term forecasts, let us say over the next season, 6 months, 1 year or 3 years, medium term forecasts, when we are talking about, we need to incorporate the periodicities in the process into the models, and that is where we use the spectral analysis. And the recent research area in hydrology, which deals with impact studies of, that is the climate change impact studies on hydrology. Such studies also require identification of periodicities, oscillations, decadal oscillations and so on in the particular process that we are talking about. So, frequency domain analysis is an important topic in stochastic hydrology. We will not go into the theoretical development of several aspects of the frequency domain analysis that we will be dealing with. Rather, what we will do is we will pick up directly the expressions that are available and then see how we apply to a hydrologic time series, how we interpret the results and how we identify the periodicities, how we check the significance of the periodicities so identified, and what do we do with these periodicities in subsequently building up the time series models. So, the first level, as I said, we express the time series x t as consisting of different frequencies. For example, in this case we take a sinusoidal representation of the time series. So, we write x t as a constant alpha naught and then summation over k to n by 2 or n minus 1 by 2, where n is the number of data points that we have. If n is even, we write the summation up to n by 2. If n is odd, you write up to n minus 1 by 2. Alpha k cos 2 pi f k t plus beta k sin 2 pi f k t summation ends here plus epsilon t. So, this is how we are expressing the time series as consisting of a sinusoidal component, a random component and a constant. For a given k, this f k here is the kth harmonic of the fundamental frequency. The fundamental frequency is simply 1 by n. So, f k is written as k by n. So, for a given k, we will have expressions for determining alpha k, you know f k, you are writing for the time period t, therefore, this t is known. Beta k, we have an expression, I will just present it, again f k is known, t is known and epsilon t is a random component. The periodicity when we write x t in this form is simply 1 by f k. So, f k is the frequency, obviously periodicity will be 1 by frequency. So, in this expression we determine alpha naught, which was a constant here, by simply the estimate of the mean, which is x bar, and alpha k we determine by this expression 2 by n t is equal to 1 to n x t cos 2 pi f k t. You are summing it over all the time periods, t is equal to 1 to n, and this is the original time series x t. F k is the particular frequency that we have determined for that particular k, that is k by n, and t is the particular time period. Similarly, beta k we determine by x t sin 2 pi f k t. Now, these expressions are in general taken up to about a maximum lag of m, and this lag typically we consider up to about 25% of the total amount of data, total number of data points that we have. So, about 25% of the data lag. These expressions for alpha k and beta k are valid up to k is equal to n by 2 as mentioned here. When n is odd, the expressions are true until k is equal to n minus 1 by 2, and the last values of alpha n by 2 and beta n by 2 will be given by this, beta n by 2 will be equal to 0. Now, let us see what are the interpretations of this. The way we have introduced the spectrum is called the variance spectrum. So, it divides the variance, that is the observed variance, into number of intervals of frequency or bands of frequency, and the spectral density, as we write here, it indicates the amount of variance per interval of frequency. So, we write the spectral density I k as n by 2 alpha k square plus beta k square, written for k is equal to 1 to m, m is the maximum lag. Similarly, we write the angular frequency, the frequency that we introduced, namely f k is equal to k by n, is now converted into angular frequency by writing it as 2 pi k by n. So, omega k here is 2 pi k by n, again written for k is equal to 1 to maximum lag. A plot of I k versus omega k on the x axis, I k on the y axis, is called as the line spectrum or simply spectrum in many cases, and it looks typically like this. So, with p as given by n by k, we have omega k is equal to 2 pi by p, p is the periodicity. Now, we plot omega k versus I k, omega k is determined by 2 pi k by n and I k is determined by this expression, alpha k is determined as earlier, alpha k is determined using this, beta k is determined using this, and therefore, we know all the terms given a time series. We can determine for various values of k the w k values, and you plot w k versus I k. This is called as spectrum in general. These are the various salient features that we must remember. The total area under spectrum, when we are talking about the variance spectrum, the total area under the spectrum is equal to the variance of the process. A peak like this in the spectrum indicates an important contribution to spectrum, that is the whole range here, this whole range we are talking about the distribution of the spectrum, distribution of the variance, I am sorry, in several bands of frequencies. So, whenever you get a peak here, this indicates that there is an important contribution to the variance of the process around these frequencies. The prominent spikes here indicate that there is a periodicity corresponding to the angular frequency that we are talking about. So, when you plot the spectrum, you capture these peaks, look at the omega k values, convert that into the periodicity, and that indicates that a periodicity corresponding to that particular time exists in the data. Now, the particular expressions that we just introduced are one among several possible expressions for spectrum estimates. So, we are using one of them. In the text and in the literature, you may find several different ways of expressing the spectrum, but we will adhere to the particular type of expressions that we have just introduced. So, essentially then what we are doing in spectral analysis is to convert the x t, which is the observed time series, into a sort of a Fourier transform, where we are using a sinusoidal representation of the time series, and then estimating the spectral density I k. We are plotting I k versus omega k versus I k, where omega k is the angular frequency, and when we plot omega k versus I k, or I k on the y axis and omega k on the x axis, we see spikes or peaks in the spectral density typically. Now, these peaks will indicate the periodicities inherent in the data. The omega k corresponding to a particular peak, you convert that into the periodicity 2 pi by omega k, and that periodicity in the time domain will indicate the periodicity that is present in the data. For example, if you are looking at monthly stream flow data and then you plot a spectrum, plot the line spectrum, Typically, you may get an omega k which corresponds to a periodicity of 12 months or maybe 6 months, 3 months, etcetera, depending on the type of stream flow data that you have. So, when we look at certain examples, these points will become clearer. We will see one example now, where first we introduce how exactly we estimate alpha k, beta k, the coefficients for a specific value of k. Remember, for a given k, f k is equal to simply k by n. N is the number of observations that you have. So, let us get an example here. This is the time series. We have 10 values here. This is just for demonstration. You have 10 values of x t. We are determining omega k and I k for k is equal to 1. Because k is equal to 1, you know f k is equal to k by n, n is 10 in this case, therefore, f k is equal to 0.1. And so, here we write t is equal to 1, x t is known 105, these are the observed values of the time series, 2 pi into 1 by 10 into t, in this case it is 1 in radians. So, cos of 2 pi f k t is 0.809, similarly sin of 2 pi f k t is 0.5878 and so on. Then we write x t cos 2 pi f k t and x t sin 2 pi f k t. What are we doing here? We are looking at this expression I k is equal to n by 2 alpha k square plus beta k square. So, for a given value of k, we determine alpha k and beta k, and for that given value of k, we are determining I k. So, the example is for k is equal to 1. So, for a given k, first determine f k by k by n and then apply these expressions. So, x t cos 2 pi f k t, x t sin 2 pi f k t, and you get summations here. Alpha k, you look at the expression for alpha k here is 2 by n x t cos 2 pi f k t, t is equal to 1 to n. So, this is the expression we are using to estimate alpha k. Similarly, for beta k we are using this expression. So, we sum this over all the n time periods and get this value. Similarly, sum this term, get this value. You get alpha k as 2 by n, which is 2 by 10 into the summation of x t cos 2 pi f k t, and you get alpha k as 3.1046. Similarly, beta k, you sum all the sin terms here, x t sin 2 pi f k t terms over t is equal to 1 to n, and you get beta k as minus 8.3698. So, for a specified k, you know how to get alpha k and beta k. Once you know alpha k and beta k for all k, you determine I k. Once you have determined alpha k and beta k for, let us say k is equal to 1 to m, m is the maximum lag, you can determine I k for all these k's, because alpha k and beta k are known. Similarly, you know omega k 2 pi k by n. So, for a given k, you know omega k and I k, plot omega k on the x axis and I k on the y axis, you will get the spectrum. So, this is how we estimate the spectrum. Now, what we are doing by calculating alpha k, beta k and then omega k etcetera, is essentially to capture the inherent periodicities in the data. So, if you have plotted a correlogram in the time domain, correlogram would have already given you some idea about existence of periodicities. Now, this will be verified in the spectral analysis, and also the information content, the information on the frequencies or the periodicities inherent in the data comes out more prominently in the frequency domain, and you can also examine the significance of the periodicities. So, you identify the periodicities and then examine the significance of these periodicities. The way we estimated the spectrum and plot of I k versus omega k that we just did is called as the line spectrum. Now, the line spectrum transforms the information from the time domain to the frequency domain. As I said, while the correlogram indicates the presence of periodicities in the data, the spectral analysis helps identify the significant periodicities themselves. We will do some examples by which we can demonstrate this fact. The line spectrum, as we had defined, is a statistically inconsistent estimate, and the plot that we get typically is not really a smooth function. You get spikes like this, and then these need not be actually 0, but there will be some lines like this, and then there is another peak and so on. So, this is not really a smooth function that we have defined. We smoothen the function and redefine the line spectrum. This is generally called in hydrologic literature at least as the power spectrum. So, the smoothened spectrum is called as the power spectrum. For the same graph, it may appear something like this. So, you may have smoothened values. This is the power spectrum as we defined just now is called as the it is a consistent estimate of the spectral density. So, we define the power spectrum this is actually a Fourier cosine transform of the autocovariance function. So, we know how to determine the autocovariance functions C k if you recall, and we transform the autocovariance function as a Fourier cosine transform and then define the power spectral function. So, the power spectrum I k is given by 2 C naught plus 2 into summation j is equal to 1 to n minus 1 by 2 lambda j C j are the autocovariance functions cos 2 pi f k into j. So, in this summation you are talking about j here. These are called as lambda j's are called as the lag windows, and there are ways of estimating the lag windows. For example, we talk about 2 key window, Parson window and so on. We will introduce one of the methods of estimating lambda j's, and all other terms are defined. So, C naught is your autocovariance function at 0, which is just the covariance. In fact, it becomes the variance, sorry. The lambda j's are estimated by what are called as there are various expressions for expressing lambda j for estimating the lambda j's. So, lambda j is equal to 1 by 2, this is given by 2 key window, and this is most commonly used. 2 key window and Parson windows, these are typically used for estimating lambda j's. We introduce the 2 key window here. So, lambda j is equal to 1 by 2 1 plus cos 2 pi by m dash. Now, this m dash is slightly different from the m that we talked about, the maximum lag. Now, m dash can also be about 0.25 n. A general guideline for m dash or the maximum lag is that it should not be too small, nor should it be too large, so that you are not missing the information content in the frequency distributions. So, typically we use about 25% of the data, and some authors also recommend 2 root n, you go up to 2 root n. If you have 100 data, 2 into root of 100, so about 20. Whereas, if you have 100 data, this may indicate about 25 values. So, typically it should not be too large, nor should it be too small. The smoothened spectrum, which is omega k versus I k, once you estimate lambda j's, you can estimate I k here, the covariance functions are known. So, you estimate the covariance functions and you can estimate I k, and omega k is the same as what we did earlier, 2 pi k by n, and you plot W k versus I k. This is called as a power spectrum. So, this will be a much smoother diagram and it is also a consistent estimate. Now, in the frequency domain analysis, the information is extracted from the frequency domain, that is from the spectrum. Let us say you have a completely random sequence. For example, you generate using your calculator a series of uniformly distributed random numbers in the interval 0 and 1, and you plot the spectral density. For a completely random sequence, you will see that the spectrum oscillates like this. That means, you are unable to get any particular peaks in the spectrum. What does this mean? This means that the variance is rather uniformly spread. There is no particular frequency band which has more variance content than any other band. Such processes are called as white noise in the spectral analysis. So, the white noise indicates that no frequency interval here contains any more variance than any other frequency interval. And you recall that if you have a purely random sequence, your rho k is equal to 0 for k not equal to 0, and this is the theoretical rho k, and if you have sample estimates R k, the R k will be all significant for all k not equal to 0. So, R k will be insignificant for all k not equal to 0. What do I mean by significance? If you recall, we draw a band of 2 by root n, actually 1.96 by root n on either side, plus 1.96 by root n and minus 1.96 by root n. This is at the 95% significance level. So, if all your R k or the lag k correlations fall within this band, they are all insignificant. So, for a purely random process, you will have all R k's being insignificant, and for a purely random sequence, if you draw a line spectrum or a power spectrum, the spectrum looks like this, which indicates that no frequency band contains any more variance than any other frequency interval that you consider. Typically, what we do is in the run up to building time series models, first we plot the time series, then we plot the correlogram. We may suspect that the correlogram indicates some frequencies or some periodicities inherent in the data. Then we would like to be sure that we remove the periodicities from the time series, because when we are building time series models, x t is equal to d t plus E t, you want to first identify the d t. Once you identify the d t, you remove the deterministic component, so that you can model only the stochastic component. To identify the periodicities, we then plot the spectrum, either the line spectrum or the power spectrum, Smoothen spectrum, and identify these periodicities. We also check for which of these periodicities that we have identified are in fact significant, so that you can use them in your models. The spectrum, as we showed just now, it shows several spikes like this, prominent spikes, which indicate that there are periodicities inherent in the data. The period corresponding to any particular value of omega k may be computed by 2 pi by omega k. So, let us say you have a spectrum like this and you identified that this is a peak and this corresponds to a particular omega k. The period corresponding to that omega k will be simply 2 pi by omega k. Then let us say that we identified that this is a period and this is significant, but we are not so sure whether this is significant, and so on. How do I test? once we know that a particular peak is significant, let us say that this periodicity is significant, we remove the periodicity corresponding to this, reconstruct the series, replot the power spectrum and then examine the periodicity for the next. So, the way we do is we test for the significance of periodicities one by one. Let us say you remove this periodicity and test for the next highest period, highest peak, remove that and test for the next highest peak and so on. So, this is the way we test for significance of periodicities. So, what do? We reconstruct the time series z t is equal to x t minus y t, in which y t is the series containing the previous periodicities. So, we reconstruct it as x t minus y t, where y t is defined as, let us say that you want to remove d number of periodicities 1, 2, 3 etcetera up to d number of periodicities. So, you write y t using your frequency domain notation as y t is equal to mu plus alpha 1 cos omega 1 t and so on. This is corresponding to the first periodicity omega 1, this term is corresponding to the second periodicity omega 2 and so on. So, you deduct terms corresponding to d number of periodicities omega d t. So, we are actually removing d periodicities through this series y t, and you are constructing z t is equal to x t minus y t with d number of periodicities removed. Typically, in hydrologic applications we remove one periodicity, two periodicities, 3 periodicities and so on, not more than that. So, we construct this series y t and reconstruct our x t, and the spectrum of new series z t is plotted and the spikes are again observed. Now, when you reconstruct this, typically what we see, again we see some prominent spikes. Let us say you removed one periodicity and then reconstructed the time series, plotted the spectrum for the reconstructed time series. You will see again significant peaks. Visually you can see that there are significant peaks. Because you have removed the earlier significant periodicities, the remaining periodicities now appear very prominently in the series, in the spectral density, spectral diagrams. Just by visually examining, we may tend to conclude wrongly that these periodicities that we are seeing are statistically significant, because they appear very prominently in the time series, in the transformed time series actually. But it is necessary for us to have statistical methods by which we can test the significance of the periodicities that we so identify, and that is what is done. We introduce a statistic gamma square n minus 2 by 4 rho 1 cap. This is given by Kashyap and Rao 1976, the reference is here. So, gamma square is alpha square plus beta square, and rho 1 cap is estimated by this. T is equal to 1 to n. This is the particular periodicity which we are examining. So, omega k as identified in your spectral analysis, you have identified a particular k, and this is the periodicity which you want to examine for significance. So, omega k is known, and t you are summing from t is equal to 1 to n. So, x t minus this particular periodicity removed, that gives you rho 1 k, and this alpha and beta are also for that particular k that you are considering. So, you know gamma square and n is known, rho 1 cap is estimated, and therefore, you know this statistic. This statistic we check against the F distribution with 2 degrees of freedom, n is the number of data points. So, if the statistic that we so computed is greater than the corresponding F value, then it is significant. The periodicity at level alpha is significant. This test examines one periodicity at a time, and it should be carried out on a series from which all the periodicities previously found to be significant are removed. So, this is done one by one. Remove the first periodicity, test for the second one, remove the second one, test for the third one, and so on. Like this you can do. Now, when we build stochastic models, for example, you are building models of the ARMA type etcetera, which we will subsequently introduce, you need the series to be devoid of any periodicities. So, you would have identified you should identify the periodicities first, remove the periodic component from the series, reconstruct the series, and then on the reconstructed model reconstructed series you build the time series models, stochastic models. So, a necessary condition in stochastic models, in most stochastic models, is that the series being modeled must be free from any significant periodicities. Now, let us say that we have identified the series consists of several significant periodicities. How do we remove these periodicities? Now, one way of doing this, that is, we want to remove all the periodicities inherent in the data. One simple way of doing it is simply standardize the series, that is equal to x t minus mu over sigma, that is the long term mean by the standard deviation. If we normalize the series and then examine the particular spectral density, you may see that most of the periodicities are removed. In many of the hydrologic applications, this standardization works, either standardization or normalization works as a first step. Then there are also techniques for differencing and so on of the series, which will remove certain deterministic components. So, in a monthly time series, for example, in this expression we may write x t minus x I bar over S I. Let us say you are talking about monthly time series, where t is equal to 1 to 12 and you are talking about the flows. Now, x I bar here indicates the mean of the particular month to which t belongs, for example, mean of the January, mean of the February and so on. Similarly, S I is the standard deviation of the month to which t belongs. So, like this we standardize the series. The series that we so standardized has a 0 mean and unit variance. So, this series is we can examine, we will do through some examples subsequently. We will examine that the z t that we so obtained by transforming x t will be in most cases devoid of any periodicities. So, we can use z t in our stochastic models. Let us look at a time series. The statistics are available, let us say the flow are available from 1979 to 2008, they will be available in this form, that is the monthly stream flow will be available in this form. I have shown only 1 year data from June to May, but like this it is available from 1979 to 2008. So, you have the series of flow observed. We plot the time series first. So, you have around 340 some odd values here. So, you plot the time series looks like this. Immediately just the visual examination of the time series indicates that there must be some periodicities inherent in the data. As you are seeing, the time series itself shows some oscillations there, and therefore, you suspect that there must be some periodicities inherent in the data. Then we plot the correlogram. How do we plot the correlogram? You know, for different k you can estimate rho k and then you plot rho k versus k. The correlogram clearly indicates that there are periodicities here. You can get the peaks of the correlation on either side, and then you can suspect that the periodicities are, let us say, corresponding to k is equal to 6, k is equal to 12, k is equal to 18 and so on. This indication that the time series and the correlogram together have given, namely that there are periodicities inherent in the data, we now confirm or reconfirm with the spectral analysis. So, we use the time series and draw the line spectrum. While the correlogram showed a smooth oscillations like this in the time domain, we convert this the time series into frequency domain and then do the frequency domain analysis, plot the line spectrum. Immediately you will see that there is one significant spike at a certain omega k somewhere around 0.5. Similarly, another omega k around 1.1 or some such thing and so on. So, the line spectrum immediately extracts the information of the frequencies and then shows that there may be a periodicity here, etc. If you recall again that what this shows is that there is a significant contribution to variance of the process around these frequencies, much more significant contribution compared to any other frequencies somewhere here. Similarly, suddenly you come across another spike where there is a significant contribution to variance around these frequencies and so on. So, these indicate that these are periodicities that are present here. This is the line spectrum, which is an inconsistent estimate, and then we also provide the power spectrum. So, power spectrum also, as you can see between the line spectrum and the power spectrum, this is a slightly more smoothened version of the spectrum, where you have a slightly broader and smoother band around which the variance, the contribution to the variance are prominent. So, we identify this particular omega k value where we are seeing the peak. In this particular case, it is 0.5236. So, this peak occurs at 0.2536 both for the line spectrum as well as for the power spectrum. And the corresponding periodicity p is simply 2 pi by omega k, where that omega k is the value of omega k corresponding to this particular peak. So, 0.5236 will be the periodicity corresponding to this will be 2 pi by omega k, which corresponds to 12 months. This is a monthly time series. So, we directly get the periodicity as 12 months. The next peak here occurs at omega k of 1.0472, this corresponds to 6 months. When you do 2 pi by 1.0472, you come to around 6. The actual value may be just 6 point something, etc., but you can say that the periodicity is 6 months. Similarly, the next one corresponds to 1.571 and that indicates a periodicity of 4 months. Next corresponds to 2.094 here, and that corresponds to a periodicity of 3 months. So, from the data, from the time series data, you now identified by doing the spectral analysis, you now identified that there is a periodicity of 12 months and 6 months, 4 months and 3 months inherent in the data. But whether all of these periodicities need to be included in our time series models, all of these are significant. Now, this needs to be tested by the test that we just indicated. So, let us say that we want to examine whether the third periodicity, we will assume that 12 months and 6 months, let us say they are significant, but we are not so sure whether the 4 month periodicity is significant, whether the 3 month periodicity is significant and so on. So, to test this, what we do is first you remove the first two periodicities that we have identified, that means corresponding to omega k of 0.5 something and omega k of 1.0 something. These two periodicities you remove, reconstruct the data, reconstruct the time series and then replot the power spectrum and then see whether these periodicities are significant. So, first we reconstruct the time series as z t is equal to x t minus y t. We are removing the first two periodicities here. So, the periodicity corresponding to omega 1 is removed here, periodicity corresponding to omega 2 is removed here, where omega 1 and omega 2 are here. This is omega 1 and this is omega 2. So, these two periodicities we are removing and then reconstructing the time series as z t is equal to x t minus y t. So, omega 1 is this and the corresponding alpha 1 is 29.28 and beta 1 is 172.93. Now, these are obtained from your earlier expressions, if you recall alpha k and beta k, they are written here. So, for a given value of alpha, for a given value of k, you know how to get alpha k, you know how to get beta k. So, k is equal to 1 in the first case. So, you determine those and retransform the series. So, this is how you determine alpha 1 and beta 1. Similarly, for the second spike that we saw in the spectral density, you have omega 2 is equal to 1.0472, you get the corresponding alpha 2 and beta 2. So, here all the terms are known. Construct y t series and then construct z t series from your original x t by deducting y t from your original x t. Say for example, for t is equal to 1, by putting all these values you get y 1 is equal to 215.5 and z 1 is equal to x 1 minus y 1. So, x 1 was in this data as you can see 54.6. So, 54.6 minus 215.5 you get minus 160.9 and so on. So, like this now you have constructed the z t series. Now, on the z t series now, this is how the time series plot of z t looks. So, initially you started with x t time series, the original observed data, you plotted the time series, you suspected that there were periodicities present in that, you plotted the correlogram which confirmed that there were periodicities, then you plotted the spectral density which brought out the periodicities corresponding to 12 months, 6 months, 4 months and 3 months. You removed the periodicities corresponding to 12 months and 6 months from the data by transforming the data z t is equal to x t minus y t, where y t is the series corresponding to the first two significant periodicities or suspected significant periodicities, and that is the series that we have plotted here now. So, this series looks something like this. Then we plot the correlogram. Now, correlogram, these are the significance bands. Correlogram looks something like this. There are some peaks here, it is still oscillating and there are some peaks which are way beyond the significance bands. We plot the power spectrum, this is how it looks. Now, the original power spectrum was somewhere here, is shown here. In the original power spectrum, there was a peak at somewhere around 0.5, there is no peak here because we have removed that. There was another peak at 1 point some value, that is also removed. So, this is corresponding to 12 months, this is corresponding to 6 months, both of them are not present here. The third peak which was occurring somewhere around 1.56 or something, that becomes prominent now. So, the effect of transformation that we did was to remove the earlier periodicities and bring out to the fore the other periodicities. So, these two become prominent now. Now, we can remove this. From this figure it appears as if this has to be significant, but we have the test that we can make for examining this significance. If we know that that is significant, remove that and then again replot the power spectrum and then check which other periodicities come up. The significance test of periodicities or the identified periodicities from the spectral analysis, how significant they are we conduct the significance test to answer that question. That we will discuss in the next lecture. So, in today's lecture what we did is we introduced the frequency domain analysis. In the frequency domain analysis, we transform the time series x t into a series consisting of typically in the way we have introduced sinusoidal terms, and then we estimate the spectral density and we plot the spectral density against the angular frequency omega k, and this gives the periodicities present, an idea of the periodicities present in the data. Then we the way we have introduced the first expression that we have introduced is called as the line spectrum, which is an inconsistent estimate, and we converted that into a power spectrum. Power spectrum is actually I am sorry, we did not convert the line spectrum into power spectrum. We introduced another expression for power spectrum, which is a Fourier transform of the covariance function, and we plot the power spectrum again I k versus omega k, and then see that there are prominent spikes. The prominent spikes that we see either in the line spectrum or the power spectrum indicate the particular periodicities. The omega k corresponding to a spike can be transformed into the corresponding periodicity by p is equal to 2 pi by omega k. So, in the monthly time series that we saw as an example, we got significant periodicity, we got periodicities, I am sorry whether statistically significant or not needs to be tested, but we got periodicities corresponding to 12 months, corresponding to 6 months, 4 months and 3 months. We remove the first two periodicities, for example, reconstruct the time series by removing the first two periodicities, redraw the power spectrum of the transformed series, and then we see that the first two periodicities are not present in the revised power spectrum, but the third one becomes prominent, the fourth one becomes prominently visible. We need to test whether the periodicities that we have so identified from the spectral density spectral analysis are in fact statistically significant. This exercise we will do in the next lecture. Thank you very much for your attention.